Greetings, geometers. 5 axioms down. We know that there is more than one point in our geometry. We know anytime there are 2 points together, there's a line, a unique line that goes through them. We know that every line is a number line. We know that lines divide the plane into 2 half planes, disjoint, non-empty, convex. And we know the protractor postulate works. So now it's time to play with triangles and how they are congruent. So this is axiom 6. This is the last axiom we talk about until like lesson 13. We can do a whole lot of geometry without even worrying about any other axioms in place. This one gets us a lot, and it's the SAS postulate. We postulate side angle side. If triangle ABC and triangle DEF are two triangles such that AB is equal to DE, BC is equal to EF, and angle ABC is congruent to angle DEF, then triangle ABC is congruent to triangle DEF. By the way, AB and DE are numbers. If you were to write segment AB and segment DE, you would use the congruent sign between them. Similarly, segment BC is congruent to segment EF. Segments are congruent, numbers are equal. Okay, so let's just establish that this has to be a thing. If we were working in the taxicab metric, and we've talked about the taxicab metric before, side angle side fails. Consider this blue triangle. This blue triangle has this side of length 2 and this side of length 2 and a right angle here. This red triangle here, well, let's see. Let's pretend this is the point 2, 0. This is the point 0, 2. So how long is this segment in the taxicab metric? We count the overs and the downs. That's 4. In the taxicab metric, this is the point 1, 0. This is the point negative 1, 0. This is the point 0, 1. So how long is this segment? Well, it's 1 and 1 is 2. And how long is this segment? 1 and 1 is 2. And that's a right angle in between them. So this triangle has side angle side, congruent to this triangle's side angle side, but the hypotenuse here has only length 2. It's in fact an equilateral right triangle. Don't even go there in the taxicab metric. So these two triangles are not congruent because their third sides are not congruent. So the taxicab metric is going to fail in our neutral geometry. We do have to postulate this, because this would be okay. This blue-red scenario would be okay with respect to the other 5 axioms, but it's not okay with respect to side angle side. So we postulate it. I have no idea why the geometers of years past have decided that this is the one that gets postulated instead of side, 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 which seems like it makes much more sense to me. But they have all the books I can find postulate side angle side. It's a little bit weird. So what does that mean? Well, that means if you have triangle ABC and triangle DEF, and this side is congruent to this one, and this side is congruent to this one, and this angle between those sides is congruent to this angle between those sides, then triangle ABC is congruent to triangle DEF. In other words, we can pick this triangle up and bring it over and put it down on top of DEF and everything matches. That's the idea. Notice the order matters. We do not say that triangle ABC is congruent to triangle DFE. That's not true. Because if we say that triangle ABC is congruent to triangle DEF, we mean that when we pick this triangle up and bring it over here and put it down on top of DEF, A sits on top of D, B sits on top of E, C sits on top of F. So there is no other way that that works. So triangle ABC is not congruent to triangle DFE because B would not sit on top of F, C would not sit on top of E. Okay? Okay. So this is what we postulate. We decide that if side angle side in one triangle is congruent to side angle side in another triangle, then the two triangles are in fact congruent. We have good reason to believe that's true. It agrees with our intuition that that's true, but we postulate it. It's not something we prove, it's something we assume. So I'll give us a quick proof here that explains how we use this. So we're going to assume that ABC is a triangle, and we're going to assume that AB is congruent to AC, and we're going to prove that angle ABC is congruent to angle ACB, and we're going to do this in two ways. Suppose triangle ABC is drawn so that segment AB is congruent to segment AC. Again, notice AB and AC are numbers. AB and AC here are geometric figures. Geometric figures are congruent. Numbers are equal. So suppose triangle ABC is drawn so that segment AB is congruent to segment AC. Construct the angle bisector of angle BAC this way. By crossbar theorem, there is a point D at which the angle bisector intersects segment BC. That happens by crossbar. So what have we got? We've got these two angles congruent because this is a bisector. We've got these two sides congruent because they are. We're going to end up with this side congruent to itself. So let's see. Let's catalog all of that. We already have these sides are congruent because ray AD is an angle bisector. Angle BAD is congruent to angle CAD. Also, AD is congruent to AD by the reflexive property. Boy, are we slowing down here. So that's sometimes denoted with an X on the diagram. So we've got two sides and the angle between them here. We've got two sides and the angle between them here. Now, triangle BAD is congruent to triangle, let's get the order right, CAD by side angle side. Then the question becomes, how do we close out the argument? How do we decide that this angle is congruent to that one? We say that that follows by correspondence. Thus, angle ABC is congruent to angle ACB B by correspondence. When you were in high school, they would have said corresponding parts of congruent triangles are congruent. Here we can say by correspondence and be done with it. But there is another way to go at this. And it's a little bit clever, actually. So you got this thing going on. Here's the other way to go at this. Notice that angle BAC and angle CAB are the same angle. So angle BAC is congruent to angle CAB. Well, why would I care about that? Then triangle ABC is congruent to triangle ACB by side angle side. Left side angle right side congruent to right side angle left side. In other words, if we picked this triangle up and put it down on top of this triangle, the A would match up with the A, the B would match up with the C would match up with the B. Thus, angle ABC is congruent to angle ACB by correspondence. That's a much slicker argument. It is not by any means the argument I would think that you would do first, but it is a slick argument. Okay, that's side angle side. Think that covers all of it. Excellent, thank you.